Welcome to linearity of the Laplace transform. So a little trick that we get here, we have our theorem essentially is the Laplace transform is a linear operator. What this means is if we wish to take the Laplace transform of a linear combination of functions. So let's say we wish to take the Laplace transform of C1 times F1 of t plus C2 times F2 of t. We can go ahead and essentially split this as C1 times the Laplace transform of F1 of t plus C2 times the Laplace transform of F2 of t. The reasoning behind this, integrals themselves can be split across addition and scalar multiples can be pulled out. Integrals that exist can be done in such a form as long as all of the sort of sections themselves exist. So this can occur assuming the Laplace transform of F1 of t and the Laplace transform of F2 of t exist. And so you could be in cases where you essentially have an infinity plus or an infinity minus infinity situation where that limit does exist, but the two individual pieces are infinity. So just something to keep in mind. Our integrals, we can split, we can pull out scalar multiples, so we get the exact same thing happening here. And assuming those individual Laplace transforms exist, then the linear combination is just the linear combination of the individual Laplace, or the Laplace transform of the linear combination is just the linear combination of the individual Laplace transforms. So for example, if we want to find the Laplace transform of f of t equals 2 times e to the negative 3t plus 5e to the 2t minus 3 sine of t, we can kind of split this into recognizable Laplace transforms. So the Laplace transform of f of t is the Laplace transform of 2e to the negative 3t plus 5e to the 2t minus 3 sine of t. And this is equal to, we can split across addition, pull out those scalar multiples. We have 2 times the Laplace transform of e to the negative 3t plus 5 times the Laplace transform of e to the 2t minus 3 times the Laplace transform of sine of t. In terms of these recognizable forms, this one here is an e to the at form. E to the 2t is an e to the at form. And sine of t is a sine of omega t form. So if we go over and look at our table of Laplace transforms, we can find those particular forms. As we found previously, e to the at taking the Laplace transform just goes to 1 over s minus a. Sine of omega t taking the Laplace transform goes to omega over s squared plus omega squared. And so those are all the pieces of information we need to take the Laplace transform of this more complicated function we started with. Working through that first one, Laplace transform of e to the negative 3t. We are doing Laplace transform of e to the negative 3t. We are just setting a equal to negative 3. So this Laplace transform should just be equal to 1 over s minus negative 3, defined for s greater than negative 3. Finding the Laplace transform of e to the 2t. we are looking at a equal to 2. So we are just looking at 1 over s minus 2, defined for s greater than 2. And then sine of t. So taking the Laplace transform of sine of t, we are just setting omega to be equal to 0, sorry, omega equal 1, not 0. So setting omega equal to 1, this therefore would just be 1 over s squared plus 1 squared, or s squared plus 1, defined for s greater than 0. So putting these all together, we had the Laplace transform of f of t was equal to 2 times the Laplace transform of e to the negative 3t plus 5 times the Laplace transform of e to the 2t minus 3 times the Laplace transform of sine of t. So we have 2 times the Laplace transform of e to the negative 3t plus 5 times the Laplace transform of e to the 2t minus 3 times the Laplace transform of sine of t. This becomes 2 times 1 over s plus 3 plus 5 times 1 over s minus 2 minus 3 times 1 over s squared plus 1. We need s greater than 0, s greater than 2, and s greater than negative 3. And so we have s greater than negative 3 and s greater than 2 and s greater than 0. And so this we can go ahead and condense down to just s greater than 2, since that satisfies all of them. So we get our Laplace transform, capital F of s is equal to 2 times 1 over s plus 3 plus 5 times 1 over s minus 2 minus 3 times 1 over s squared plus 1. So this is another trick how we can break up our functions and take individual little pieces of the Laplace transform using that table of Laplace transforms.